Hello, chemist. Jolly here. Hey, this is the videos that I promised you on each of the individual topics. So this specific one is going to be on the introduction to kinetics. So I'm going to go over to our notes, okay? And we're just going to talk through each piece, and I'll try and keep each video pretty short so that you can just look at individual pieces. All right, generically, what in the world is kinetics and why do we care? So kinetics helps us answer one of the three big questions, which are what will be formed, how much will be formed, and how fast will it formed. All right, so these two we pretty much answered in Chem 111. We are going to talk a little bit more about what could be formed. There's new reactions in Chem 112, but those are the basics that we got last semester. But if it takes a million years for any of those reactions to happen, not really useful. So we need to ask the question, well, how fast will it form? And that is the study of kinetics. So the study of the factors that govern how rapidly a reaction occurs. Now, I want you to know that I'm going to use the word rate over and over and over. It is the same word. I'm just going to put different additions to it so that you can tell which piece I'm talking about. But the study of kinetics is all about the rates of reactions. Or you could just say rate, or you could say reaction rate, whichever. But it is the speed at which a reaction occurs. One huge thing, it is always a positive quantity, always positive. You can have negatives in front of it, but negatives, it doesn't mean you go in the whole rate, okay? You're not going back in time. It just means that it's being used up, or usually that means a reactant. So generically, the rate is the change in concentration over the change in time. And so the brackets indicate molarity. Delta means change in, and change in time. And the time can be, pretty much anything, but seconds and minutes are the most common for us. Now, technically, the concentration can also be anything, but we're in chemistry, and so molarity is our concentration of choice. The first equation that I want you to recognize is called the reaction rate equation. Keep in mind, it's just a rate equation, but the way I'm going to let you know that I'm talking about this one, I'm going to call it the reaction rate equation. So when I say that, this is the one that I want you to think of. And it is going to relate together all the species in a reaction with their coefficients. All right, so how are we going to do this? Okay, there's a nice generic one right here. So you would put the word rate, and this is an equal sign. Okay, so the rate is equal to the change in the concentration of A, but we're going to take into account the coefficient. And the negative means that it's a reactant or it's being used up. That is also equal to the change in the concentration of B. It's being used up and its coefficient. Now these two are products, so that's why you can either put the plus or it's implied. And again, it's coefficient and it's coefficient. So you can come up with an equation for any reaction using this formula. Always remember, the reaction rate is always positive. The negative is just implying that it's being used up or a reactant, okay? That's what the negative sign means. So let's do an example with a real equation. So we have some N2O5 and it's breaking down into two NO2s plus 1/2 oxygen. So the way we would write it is the rate equals the change in the concentration, and the reactant is N2O5, over the change in time. It is a reactant, so I'm going to put the negative, and then its coefficient is 1. And so you don't have to write the 1, of course, but it's implied there. That is equal to the change in the concentration of the first product over delta T, and then I need to take into account its stoichiometry, its coefficient, so I put the 2, and you don't have to put the plus, but it's a product, so it's being formed. And then this is the one I really want to point out. Can I put a half under there? Yes, but mathematically that is the same as this. The change in the concentration over the change in the time, because if you invert a half, the 2 comes to the top. Right, so that is the generic reaction rate equation. Now we need to be able to put some numbers with it, okay? We need to put some numbers with it. So here's my equation. 1 nitrogen plus 3 hydrogens goes to 2 ammonias. Can I write, can I write a reaction rate equation for it? Yes. The rate is equal to the change in the concentration of the N2 over the change in time. It's disappearing, so I'm putting the negative, and its coefficient is 1. That is the same as, again, it's a reactant, the change in the concentration of the hydrogen over delta T, and its coefficient is 3. And this is a product, so the change in the concentration of ammonia over delta T, and there's a 2. All right, there's my equation. Can I use it now? Why, yes. If nitrogen disappears at a rate of 0.10 moles per liter per minute, what are the rates of the hydrogen and the ammonia? Now, I'm going to go over the whiteboard so that I have more room, but I needed this number. Okay, so you have to be able to get that number somewhere in order to be able to do these problems. So whiteboard, erase it from organic. All right, so here's my rate of reaction equation. All right, so there's just taking into account the reactants and the products, and we do know that it was N2 plus 3 H2s goes to 2 NH3s. And so I need a 1 right here, I need a 3 right here, and I need a 2 right there. And I'm going to have to peek because I already forgot what rate I gave you in that problem. So let me go out of this, back into my notes real quick. All right, nitrogen disappears at 0.1. You'd think I could have remembered that for that long. All right, so I know the rate of nitrogen. Okay, that's one way to write it. Or the change in the concentration of nitrogen. Another way to write it is 0.10 molarities per minute. Now I do know it's disappearing, so I'm going to put a negative. Remember, that doesn't mean I'm going in the hole, it just means it's disappearing. Okay, can I use that number? Well, sure. I want to find all of the others. So you just take this algebra equation and you plug it in. So I'm going to say a negative. You know what? Before I do that, I want to highlight some things. That is the actual rate. So all of those letters and symbols, that is the rate. So don't forget that. So the negative rate of N2 divided by 1 is equal to the negative rate of H2 over 3. Okay, that's another way to visualize it. And I know this piece. Okay, so I'm going to plug that in, a negative 0.10 molarities per minute. So if I want to solve for the rate of hydrogen, I'm going to multiply both sides by 3. So my 3 goes away, and I'm going to divide both sides or multiply both sides by a negative. So one of those is gone. And I'm going to end up with a negative 0.30 molarities per minute. Does that make sense? Well, yes, we know that the hydrogen has to disappear 3 times faster than the nitrogen. So the negative means it's disappearing. Okay, we know this is a ratio or a comparison to the nitrogen. And so that makes sense. So there is that one. So the change in the nitrogen over time is equal to a negative 0.10 molarities per minute. We just found that the change in the hydrogen per time is a negative 0.30 molarities per minute. Now I'm going to find the last one using the hydrogen just so that you can see it works across the board. That really is an equal sign in the equation. So I'm going to take a negative 1/3 times my rate of hydrogen is equal to 1/2 times the ammonia. Now, I wrote it this way just in case that helped you visualize what was going on right here. Because remember, that really is 1/2, and this really is 1/3. So if it helps you to visualize taking those out front, absolutely do that. Okay, well, zero point 0.3 divided by 3 goes back to 0.1, so a negative and a negative. This becomes 0.10 molarities per minute is equal to 1/2 the rate of ammonia. I'm going to multiply both sides by 2, and the answer is, whoops, I was going to put 2.0 molarities per minute. And so we know the rate of ammonia is a positive 0.20 molarity per minute. Excellent. Excellent. All right. There is your basic understanding of the rate of reaction equation, and its power is it uses all of the species in an equation and it relates them together using their coefficients. And don't forget, it still equals this word rate. So the overall rate of the reaction is also 0.10 molarities per minute. And remember, overall rates, they are never negative, and so that's why it came out to be a positive. All right, head back to our notes, make sure that covers everything we need there. All right, that is the rate of reactions, and until next time, jolly out.